Welcome to the deep dive, where we really try to unpack complex ideas and hopefully give you that aha moment.
That's the goal.
Today, we're diving into something, well, incredibly small, but just immensely powerful in our bodies.
Mhm.
The proton, the hydrogen ion, H plus 3.
Tiny things, right. But they run the show.
Exactly. I mean, despite their tiny concentration, they fundamentally impact nearly every single biochemical reaction, every physiological process that keeps us alive and, thriving, from your heart beating to your brain thinking.
It's quite amazing, really. If we
Right.
didn't have precise control over these protons,
Yeah.
our internal world would just fall apart. Chaos.
Yeah.
They're like the hidden conductors of the orchestra.
Well put. So our mission today, our deep dive, is all about navigating this complex, absolutely critical world of acid-base physiology.
Mhm.
We're drawing heavily from Boron and Boulpaep's Medical Physiology, a fantastic resource, and we're going to distill those really detailed insights into explanations that are clear, engaging, and crucially clinically relevant for you.
Yeah, the aim is to make this manageable, right? So you feel confident tackling it.
Exactly. We want to give you that solid foundation. We'll look at buffers, the powerhouse CO2 bicarbonate system, how they interact, and even how our cells manage their own internal pH. So to really get this, we need to start at the beginning. What even is an acid or a base in this biological context?
Okay, good starting point. So the Brensted definition is pretty straightforward. An acid is just something that can give away a hydrogen ion, an H plus ping, think acetic acid like in vinegar.
Okay, a proton donor.
Precisely.
Hmm.
And a base, or alkali, does the opposite. It accepts that H plus is big. Ammonia is a classic example.
And you mentioned these H plus concentrations. They're not the same everywhere in the body, are they? I mean, the stomach is famous for being acidic.
They're wildly different. The range is enormous. Gastric juices can have H plus concentrations over 100 millimolar, but then pancreatic secretions, less than 10 nanomolar. That's a huge spread.
Wow. So how do we talk about that easily?
That's where the pH scale comes in, thanks to Sorensen. It simplifies things massively. pH is just the negative log base 10 of the hydrogen ion concentration.
So inverse relationship. Lower pH means more H plus set.
Exactly. And what's really key to grasp is the log scale. A 10-fold change in H plus concentration is just a 1 pH unit shift.
Only 1 unit for 10 times the ions.
Right. And even a 2-fold change in H plus Y, that's only about a 0.3 pH unit change. It compresses this huge range into manageable numbers.
Okay, but here's the critical part for anyone in medicine or biology. Why are these small pH changes, like even 0.1 units, such a big deal physiologically?
Because so many crucial molecules in our bodies, enzymes, receptors, ion channels, even structural proteins, have parts that are incredibly sensitive to pH.
Their shape changes.
Exactly. A tiny pH shift alters their electrical charge, changes their conformation, their 3D shape, and that directly impacts how well they work, their biological activity.
Can you give an example?
Sure. Take phosphofructokinase. It's a key enzyme for breaking down sugar for energy. Its activity can drop by like 90% with just a 0.1 pH unit decrease. That's huge.
90%, just from 0.1 pH.
Yeah. And things like cell growth are also highly sensitive. Basically, our cells are constantly working to keep their internal pH stable because their machinery depends on it. Most of our body fluids are actually slightly alkaline, slightly basic, compared to pure water at body temp. Arterial blood plasma, for instance, normally sits right around pH 7.4, very tightly controlled.
Okay, so given how sensitive everything is, how does the body maintain this stability? That must involve buffers, right? What exactly do they do?
Think of buffers as chemical shock absorbers. They're substances that can reversibly grab onto H plus or release H plus.
Reversibly, that's important.
Crucial. They don't stop pH changes completely, but they massively minimize the swing, like a sponge, soaking up extra acid or releasing some if things get too basic.
So it's usually a pair, a weak acid and its partner, the conjugate base.
That's a typical setup, yes, like ammonium, NH4+, and ammonia, NH3, or carbonic acid, H2CO3, and bicarbonate, HCO3, or the phosphate pairs.
And how do they work in practice? Say if some strong acid gets in.
Okay, so if a strong acid like hydrochloric acid, HCl, hits the system, the basic part of the buffer pair immediately reacts with most of those incoming H plus ions. It binds them up, preventing a sharp drop in pH.
And if a strong base comes along, like sodium hydroxide.
Then the acidic part of the buffer pair steps up. It releases its H plus ions to neutralize the added hydroxide ions, OH, again minimizing the pH rise.
And we can quantify this buffering ability. I think I've heard the term buffering tower.
We can, yes. Buffering power, often symbolizes beta, basically tells you how much strong acid or base you can add to 1 liter of a solution before the pH changes by 1 full unit.
So a higher beta means a better buffer.
A stronger buffer, exactly. For instance, whole blood has a pretty good non-bicarbonate buffering power, around 25 millimole per pH unit. But if you just take the plasma part without the blood cells, it's much lower, maybe only 5.
So the stuff inside the cells, like hemoglobin, really contributes a lot.
A huge amount, especially hemoglobin. It's a major non-bicarbonate buffer in blood.
Okay, so we have these non-bicarbonate buffers, but isn't there one system that's considered like the most important one in the body?
Yes. That would definitely be the CO2 bicarbonate pair, the dynamic duo.
What makes it so special?
Its real power comes from the fact that CO2 is a gas. It's volatile. Our lungs are incredibly good at controlling the level of CO2 in our blood plasma, keeping it remarkably stable. And that stability is key to how effective this buffer is.
How does CO2 being a gas translate into buffering power?
Well, think about Henry's law. The amount of CO2 dissolved in your blood is directly proportional to the partial pressure of CO2, the PCO2, which your lungs control.
Okay, so breathing controls dissolved CO2.
Right. And in the body, that dissolved CO2 reacts with water. It's a slow reaction on its own, forming carbonic acid, H2CO3. But then that carbonic acid quickly breaks down into H plus and bicarbonate, HTO3.
You said the CO2 reaction is slow.
It is, chemically. But inside our red blood cells, there's an enzyme called carbonic anhydrase. It speeds up that CO2 hydration step by like 1,000,000 times, massively faster.
Wow. Okay, so all these reactions kind of link up.
They effectively combine into a single, very dynamic pseudo-equilibrium.
And this is where that famous equation comes in. Henderson-Hasselbalch.
Precisely. It wraps it all up beautifully. Basically says pH equals a pK of the system plus the logarithm of the ratio of bicarbonate concentration to dissolved CO2 concentration.
So pH, pK plus log, HCO3, CO2.
That's the one. And if you plug in the normal body values of pK around 6.1, bicarbonate around 24 millimolar, and dissolved CO2 corresponding to a PCO2 of 40 millimeters of mercury, guess what pH you get?
7.4.
Bang on, 7.40. So the absolute core message here isn't about the total amount of bicarbonate or CO2, but about their ratio. That's what determines the pH.
You mentioned the system is incredibly strong. Does that depend on anything else? You mentioned open versus closed systems earlier.
Yes, absolutely crucial distinction. A buffer's effectiveness depends on 3 things. Its total concentration, the pH relative to its pK, and whether the system is open or closed.
Okay, what's a closed system?
The closed system is one where none of the buffer components can get in or out. Imagine phosphate buffers in the sealed test tube. In these systems, the buffering power is highest when the pH is exactly equal to the buffer's pK. Most of those non-bicarbonate buffers in our body, like proteins and phosphates, behave essentially like closed systems.
But the CO2 bicarbonate system in our blood, that interacts with our lungs, right? So that's open.
Exactly. It's the quintessential open system. Because CO2 is gas, it can freely equilibrate with the air in our alveoli in our lungs. This means our breathing effectively fixes the concentration of dissolved CO2, no matter how much is being produced or consumed by the buffering reaction.
And that's what makes it so powerful.
That's the secret sauce. Let's take an example. Imagine somehow 10 millimoles of strong acid, like HCl, get dumped into a liter of your blood. In this open system, bicarbonate ions, HCO3, will immediately react with almost all that added H plus I, neutralizing it. But here's the key. This reaction produces carbonic acid, which breaks down into water and CO2.
And the CO2.
Doesn't build up. Because the system is open, your lungs just exhale that extra CO2. It vanishes into the atmosphere.
So the reaction product that would normally limit the buffering just leaves?
Precisely. So the pH barely drops, maybe from 7.40 down to only, say, 7.17.
Yeah.
Almost all the added H plus gets buffered with minimal pH change. It's incredibly efficient.
That is remarkable. The lungs act like a pressure release valve for acid.
Perfect analogy. And it works the other way, too. If you add a strong base, CO2 can effectively be drawn in from the lungs or metabolism to react and replenish the H plus needed to neutralize the base.
So this openness gives it a huge advantage.
Immense. The buffering power of the open CO2 bicarbonate system in normal blood is around 55 millimolar per pH unit. That's more than double the power of all the non-bicarbonate buffers combined. It accounts for over 2/3 of the total blood buffering capacity.
Wow. So contrast that with if it were closed.
If it were closed, its buffering power at normal pH would be tiny, maybe only around 2.6 millimolar per pH unit. Being open makes all the difference.
And clinically, does this matter?
Hugely. Think about ischemia. When blood flow to a tissue is cut off, suddenly CO2 can't escape. The system becomes poorly open or effectively closed.
Ah, so the tissue loses that powerful buffering.
Exactly. And that makes ischemic tissue extremely vulnerable to large damaging drops in pH as metabolic acids build up.
Okay, that makes sense. So we understand the buffers now. Let's talk about when the balance gets tipped acid-base disturbances. What happens if the primary problem is with CO2 levels?
We generally call those respiratory disturbances. If your partial pressure of CO2, your PCO2, goes up, maybe it doubles from the normal 40 to 80 millimeters of mercury, that's respiratory acidosis.
Acidosis because pH drops.
Right. And respiratory, because the root cause is usually related to the lungs. Maybe ventilation is decreased, like in a drug overdose, or there's impaired gas exchange. The H plus concentration nearly doubles, but bicarbonate doesn't change much initially.
And the flip side, if PCO2 drops...
That's respiratory alkalosis. If PCO2 halves, say from 40 down to 20, pH goes up. Alkalosis. This often happens with hyperventilation, maybe from anxiety, high altitude causing hypoxia, or even certain drugs like aspirin in overdose.
Okay, so that's when CO2 is the main driver. What if the primary change is in bicarbonate?
Then we call it a metabolic disturbance. If your bicarbonate level doubles, maybe going from 24 up to 48 millimolar, or if you add a strong base, that's metabolic alkalosis.
It goes up again.
Yeah, pH rises. Because remember, in that open system, any extra CO2 formed just gets blown off by lungs, keeping PCO2 pretty constant initially. Clinically, you might see this with excessive bicarbonate administration or loss of acid, like from severe vomitings.
And the opposite, metabolic acidosis.
That's when bicarbonate drops. Maybe it halves, or you add an acid other than carbonic acid, like lactic acid or keto acids, or you lose bicarbonate itself. That's metabolic acidosis. pH falls. Lots of possibilities. Kidney failure is a big one. Diabetic ketoacidosis, lactic acidosis from shock or intense exercise, even severe diarrhea where you lose a lot of bicarbonate.
So it really drives home that point, doesn't it? Blood pH is this balancing act between the kidneys managing bicarbonate and the lungs managing CO2.
Absolutely. Someone once whimsically put the Henderson-Hasselbalch equation as pH is proportional to kidney over lungs.
Yeah.
A bit simplistic, but captures that dual control perfectly.
Okay, now, in reality, things are mixed, right? You've got the CO2 bicarbonate system and all those non-bicarbonate buffers like hemoglobin working together. Trying to calculate the exact outcome sounds hard.
It gets mathematically very complex very quickly, which is why clinicians rely on a fantastic graphical tool, the Davenport diagram.
A diagram? How does that work without seeing it?
Imagine it like a map for acid-base status. The horizontal axis, the x-axis, represents pH. The vertical axis, the y-axis, represents the bicarbonate concentration, HCO3.
Okay, pH on the bottom, bicarbonate going up the side. What's on the map itself?
You'll see a series of curved lines sweeping across the map. These are called CO2 isopleths. Iso meaning same, pleth meaning quantity. Each line shows all the possible combinations of pH and bicarbonate you could have at one specific fixed partial pressure of CO2.
So there's a line for PCO2 of 40 and one for 80.
And 20. Exactly. The line for normal PCO2, 40 milliliter Hg, passes right through our normal starting point, pH 7.4 on the bottom axis, and bicarbonate 24 millim on the side axis. Lines for higher PCO2, like 80 millimeter Hg, sit above the 40 line. Lines for lower PCO2, like 20 millimeter Hg, sit below it.
Got it. Contours of constant CO2. Is there another important line?
Yes, there's one more key line, typically drawn starting from that normal point. It's called the non-HCO3 titration line, or sometimes the buffer line. It's usually drawn as nearly straight in the physiological range.
And what does that line represent?
Its slope represents the buffering power of all the other buffers in the blood. Hemoglobin, proteins, phosphates, all lumped together. It shows how pH and bicarbonate would change if only those non-bicarbonate buffers were acting, usually in response to adding or removing CO2.
Okay, map laid out. How do we use it? Let's take that respiratory acidosis example again. PCO2 doubles from 40 to 80.
Right. You start at the normal point, pH 7.4, HU3 24 on the PCO2 40 line. Now, because the immediate change is just adding CO2, the system moves along that non-HCO3 titration line. You follow that line upwards and to the left, decreasing pH, until you hit the contour line representing the new PCO2, the 80 millimeter Hg isopleth.
And where you land is the new state.
Exactly. That intersection point tells you the new equilibrium pH and bicarbonate concentration. For example, it might land at pH 7.19 and bicarbonate 29.25 millimeter. The diagram visually shows that the pH didn't drop as much as it would have without those non-bicarbonate buffers, because moving along that line forced bicarbonate levels to rise somewhat.
The the non-bicarbonate buffers essentially force the conversion of some of that extra CO2 into bicarbonate, cushioning the pH fall.
Precisely. And the steepness of that non-HCO3 line depends on things like hemoglobin concentration. Anemic patients have a flatter line, less buffering. Polycythemic patients, a steeper one.
Okay, makes sense for respiratory changes. What about metabolic ones? Say adding 10 millimole of acid, but PCO2 stays fixed at 40.
This is a bit more complex to trace mentally. Start at the normal point again, pH 7.4, HCO 324, PCO2 40. First, imagine the direct effect of adding acid. It consumes bicarbonate. So mentally, shift your point straight down on the bicarbonate axis by 10 units from 24 to 14.
Okay, imaginary point at pH 7.4, HCO 314.
Right. Now, from that imaginary point, you need to consider the combined buffering. You trace a line that is parallel to the original non-HCO3 titration line. Follow this new parallel line until it intersects with the original PCO2 isoplith you started on the 40 millimeter HT line, because PCO2 is fixed in this scenario.
So drop down for initial bicarbonate consumption, then slide along a parallel buffer line back to the original PCO2 contour.
That's the concept. Where that parallel line hits the PCO2 40 isoplith is your final state. It might be, say, pH 7.26 and bicarbonate 17.4 millimole. The diagram helps you visualize how much of that added acid was handled by bicarbonate directly, the initial drop, and how much involved interactions with the non-bicarbonate buffers, the movement along the parallel line.
It's quite an elegant way to see the interplay.
It really is. And it works similarly for adding base, metabolic alkalosis. You'd shift up initially, then follow a parallel line back to the fixed PCO2 isoplith. It's a powerful tool for understanding these complex interactions without heavy math. Now, a crucial point is that the body doesn't just sit there when there's a disturbance. It actively fights back. It tries to compensate to bring the pH back towards normal.
Ah, okay. So these primary disturbances we talked about trigger secondary responses.
Exactly. Let's say you have that persistent respiratory acidosis, high PCO2. If it lasts for a while, the body doesn't just accept the low pH.
What does it do?
The kidneys step up. They start working harder to excrete more acid into the urine and, importantly, to generate and reabsorb more bicarbonate back into the blood.
So the kidneys create a metabolic alkalosis to counteract the respiratory acidosis.
Precisely. It's a compensatory metabolic alkalosis. This added bicarbonate helps to raise the plasma pH back towards that magic 7.4 mark.
Can it get all the way back to 7.4?
Sometimes, yes. If the compensation is so effective that the pH returns fully to 7.4, even though the PCO2 is still high, that specific state is called isohydric hypercapnia. Isohydric meaning normal pH, hypercapnia meaning high CO2.
And if it was respiratory alkalosis, low PCO2.
The kidneys do the opposite. They excrete less acid and reabsorb less bicarbonate. This creates a compensatory metabolic acidosis, helping to lower the elevated pH. Perfect compensation here would be isohydric hypocapnia.
Okay, so that's metabolic compensation for respiratory problems. What about the other way around? Respiratory compensation for metabolic issues.
That happens too, and often much faster, because breathing can change rapidly. If you have a metabolic acidosis, low pH, low bicarbonate, your respiratory system senses this.
And does what? Breathe faster.
Exactly. It increases alveolar ventilation. You start breathing faster and deeper. This blows off more CO2, lowering your PCO2.
Creating a respiratory alkalosis to fight the metabolic acidosis.
You got it. A compensatory respiratory alkalosis.
So from metabolic alkalosis, high pH, high bicarbonate.
The respiratory system does the opposite. It decreases ventilation. You breathe more slowly and shallowly, which causes CO2 to build up, raising PCO2. A compensatory respiratory acidosis.
Does that compensation work as well?
It often runs into limits. You can only slow your breathing so much before your oxygen levels start to drop dangerously low, or your CO2 gets so high it causes other problems. So respiratory compensation for metabolic alkalosis is often less complete than for acidosis.
So it's this whole interplay, immediate buffering, then slower renal compensation, faster respiratory compensation, all working together.
It's a beautiful coordinated response involving extracellular fluids, the cells themselves, kidneys, and lungs.
And I bet the Davenport diagram helps visualize these compensated states too.
Absolutely. It's incredibly useful clinically. You plot the patient's measured pH, bicarbonate, and PCO2. Where that point lands on the map tells you the whole story.
Like what categories?
Well, first, is it right in the middle? That's normal. Or does it fall along that non-HCO3 buffer line, but off the normal PCO2 40 line? That indicates a primary uncompensated respiratory disturbance.
Okay.
Or does it fall along the PCO2 40 line, but off the non-HCO3 buffer line? That's a primary uncompensated metabolic disturbance.
Makes sense. What else?
Then you have the regions between those lines. If the point falls into specific zones, often shown in color on diagrams, it indicates a partially compensated disturbance. The body is fighting back, but hasn't fully corrected the pH yet.
And the perfectly compensated states.
Those points would land right back on the vertical line representing pH 7.4, but they wouldn't be at the normal starting point. They'd be higher up or lower down on that pH 7.4 line, representing those isohydric hypercapnia or hypocapnia states we mentioned. Perfectly compensated.
And more.
Finally, the point might fall into regions that indicate compound disturbances where you have, say, both a respiratory acidosis and a metabolic acidosis happening at the same time, often making the pH deviation even worse. The diagram provides a rapid visual diagnosis of the entire acid-base picture.
You know, we focused a lot on blood plasma pH because, well, that's what we measure easily. But where does the real action happen? Inside the cells, right?
Absolutely. That's where most of the biochemistry of life occurs.
Yeah.
So regulating intracellular pH, what we call Phi, is arguably even more critical.
Would you even measure that?
We can, yeah. There are techniques using special fluorescent dyes, tiny microelectrodes, even sophisticated MRI methods to monitor PI in living tissues or cells. It's vital research.
So how do cells control their internal PI? What are the mechanisms?
Cells have specialized protein machinery, transporters, embedded in their membranes. Two key players are prototypes. One is the NAH exchanger. Think of it as an acid extruder. It pumps H+ out of the cell using the energy from the sodium gradient, and that raises the internal pH.
Okay, pushes acid out. What's the other one?
A common counterpart is the ClHCO3 exchanger. This one acts as an acid loader. It effectively brings acid into the cell by swapping chloride ions coming in for bicarbonate ions going out. This lowers the internal pH.
So you have an acid extruder and an acid loader working against each other.
Exactly. They create this dynamic balance, a steady state PI, kind of like a thermostat maintaining temperature.
So what happens if a cell suddenly gets hit with an acid load internally? Maybe from intense metabolic activity.
Okay, so if acid builds up inside, PII immediately drops. An intracellular metabolic acidosis. But here's the cool part. Unlike just leaving acid in a beaker, the cell's PII doesn't just stay low. It starts to spontaneously recover back towards its normal set point because those transporters react. The low PI actually stimulates the NAH exchanger, the acid extruder, to work harder. At the same time, the low PI inhibits the ClHCO3 exchanger, the acid loader.
Ah, a push-pull system. Boost the acid removal, slow down the acid entry?
Precisely. It's an elegant feedback loop that actively pushes PI back up. And interestingly, the pH outside the cell matters too. If the extracellular fluid is also acidic, it makes it harder for the cell to pump H+ out, slowing down that PI recovery.
And if the cell gets an alkaline load instead, PI goes up.
Same principle, opposite effect. If PI rises too high, the cell activates its acid loading mechanisms, like the ClHCO3 exchanger, which works better at high PI, and it simultaneously inhibits the acid extruders, another push-pull mechanism, this time working to bring the high PI back down.
Okay, that makes sense. Now, there's this clinical observation connecting potassium levels and acid-base status, like acidosis causing high potassium, hyperkalemia. Is that a direct swap, a KH exchanger?
It's a well-known link. And while some very specialized cells, like in the kidney, do have direct HK pumps, HKAT passes, the general phenomenon seen in most tissues isn't usually due to a direct one-for-one K for H swap.
So what causes it then?
It's often more indirect. For example, high extracellular potassium, hyperkalemia, can make the cell membrane less polarized, which might indirectly stimulate bicarbonate uptake into the cell, making the inside more alkaline, raising PI. Conversely, extracellular acidosis can lower PI, which might inhibit channels that normally take up potassium, leading to a net release of K+ from cells.
So the link is real, but the mechanism isn't necessarily a simple exchanger.
Exactly. It's more about how changes in pH and ion gradients influence multiple transporters and channels, leading to those observed shifts in potassium. Calling it a KH exchange can be a useful clinical shorthand sometimes, but the reality is more complex.
So clearly, intracellular pH and extracellular pH are connected. How tightly?
They are definitely intertwined. The pH outside the cell, pH changes. The pH inside, PII, usually changes in the same direction, but typically not by the same amount. Maybe PI changes only 20% to 60% as much as PI showed it.
So cells help buffer the outside too.
They do. They actively participate in taking up or releasing acid-base equivalents to help buffer the entire extracellular environment. Ultimately, the body puts so much effort into regulating blood plasma pH precisely because that enables the cells to then effectively regulate their own internal PI, Blood pH is a vital sign for cellular health.
Let's trace that connection. What happens inside a cell if the outside suddenly becomes acidic due to high CO2, like in that respiratory acidosis scenario?
Okay, good example. Boron and Boulpaep describe three phases. First, when extracellular CO2 rises, it rapidly diffuses into the cell.
Hmm.
Inside, carbonic anhydrase quickly converts it to H plus and HCO3. This causes an immediate sharp fall in intracellular pH, EII. It's like an intracellular respiratory acidosis happening almost instantly.
Phase 1, PI high drops fast. Then what?
Phase 2. You might expect the cell's acid extruders to kick in strongly, like we discussed for an internal acid load. But the extracellular acidosis that accompanies the high CO2 actually inhibits those acid extruders from working well. So there's only a very feeble partial recovery of the PI. The cell is fighting against a headwind.
So the external environment limits the internal recovery. What's phase 3?
Phase 3 happens much later, maybe over hours or days. This is when the renal compensation kicks in, remember. The kidneys start adding bicarbonate back to the blood, causing the extracellular pH to slowly rise back towards normal. As the extracellular environment improves, the inhibition on the cell's acid extruders is lifted. Now they can work properly again, leading to a delayed parallel recovery of PI, along with the recovery of extracellular pH.
Wow. So intracellular pH is really tied to what's happening outside and the body's overall compensation efforts.
Deeply interconnected.
Yeah.
The body defends blood pH so fiercely, primarily to create a stable environment that allows individual cells to maintain their own internal pH within the narrow range needed for life.
What a journey. Okay, let's try and quickly recap. We started with the proton, H plus A, this tiny ion with huge impact.
And how pH is just a way to talk about its concentration.
Then we looked at buffers, the chemical sponges, like proteins and phosphate, that minimize pH swings.
And the star player, the CO2 bicarbonate system, whose power comes from being an open system thanks to the lungs venting CO2.
Right, which makes it incredibly effective compared to closed systems. We explored what happens when things go wrong, respiratory acidosis alkalosis driven by CO2 changes.
And metabolic acidosis alkalosis driven by bicarbonate or other acid bases.
We visualized these interactions using the concept of the Davenport diagram, that map of pH viscous bicarbonate with CO2 contours.
A really useful clinical tool.
And we saw how the body fights back with compensation kidneys adjusting bicarbonate, lungs adjusting CO2, trying to restore that crucial pH balance.
Leading to those partially or fully compensated states, also visible on the diagram.
And finally, we peeked inside the cell, understanding why intracellular pH is so critical, and how cells use transporters like the NANH and ClHCO3 exchangers to regulate it, constantly interacting with the extracellular environment.
It's a complex picture, but hopefully breaking it down step by step makes it feel more manageable. Mastering physiology like this is definitely achievable.
Absolutely. Taking the time to understand these fundamental processes is a huge step, and breaking down dense material like boron and Boulpaep is key to building that confidence.
You really can get this.
So here's a thought to leave you with. We've seen these sophisticated, multi-layered compensation systems buffering respiratory, renal, cellular. What might happen clinically when multiple of these systems are compromised at the same time? And if you had to pick just one single clinical measurement in an emergency, which one do you think gives the most immediate red flag about the severity of an acid-based disturbance?
Something interesting to mull over.
You're doing great work digging into this. Keep at it. You are part of the Deep Dive family, and you are absolutely capable of mastering this material.